We're now going to look at solving linear equations, systems of linear equations. So we'll start with something called back substitution. The name will become clear shortly. So here's the idea. We have a matrix, R. It's upper triangular with non-zero diagonal entries. Now that means that R is invertible. We've already discussed that. And so we're going to write out the equation Rx equals B. And of course, what we're actually calculating here, if we're going to solve for x, is we have x equals R inverse B. I can write this because R is invertible because it's upper triangular with non-zero diagonal entries. Okay, so I'm going to write this out in scalars, and this is basically, R is upper triangular, so it looks like this. It's R11x1 plus R12x2, and so on. That's the first equation. And the first equation, notice, involves all the variables, x1, x2, x3, all the way up to xn. The second equation, by the way, involves only the variables x2, x3, x4, up to xn. That's because it's upper triangular. And the last equation, that's right down here. Pretty simple. It simply only involves xn, right? The penultimate equation only involves xn minus 1 and xn. Now, what we want to do, to calculate x, we want to basically solve for x. So let's start from the last equation. From the last equation, you see Rnn xn equals Bn. Now, these are just numbers, right? Oh, and not only that, and this is critical, we know that Rnn is not 0. And so that tells us immediately that we just divide, and we get xn equals Bn over Rnn. Now we know xn. Okay. Now, from the second to last equation, let's focus on that one. It says Rn minus 1 n minus 1 xn minus 1 plus Rn minus 1 n xn equals Bn. But you know what? We know xn. So what we're going to do is we're going to take this equation, and we're going to write xn is the right-hand side, Bn minus 1, minus this part. Now, we already know that part, this thing, because we just calculated xn divided by Rn minus 1, Rn minus 1. And again, we can do that because Rn minus 1, comma n minus 1 is a diagonal entry of R, and it's assumed to be non-zero. So I get xn. And then basically we just continue this. Now we know, after this step, we know xn, and we know xn minus 1. Now we get xn minus 2, then xn minus 3, and eventually we end up with x1. Okay, so it's called back substitution for the obvious reason is we're going backwards. We're first calculating xn and then substituting in known values into the formulas, and then just analytically working out what the various x's are in backward order. Okay, so this is the idea, and it's going to compute x equals R inverse B. So we now have a perfectly good way to do that. Let's talk about the complexity, like how long does this take? Well, the first step is, you have to divide, it's whatever it is, it's Bn divided by Rnn, that's one flop, one division. The second step is over here. Let's see what we got to do. We got to multiply these two numbers. We got to do a subtraction and then maybe a division. So maybe that's 3 flops here. Okay, so the second step needs 3 flops. And the ith step, the third step needs 5 flops, then 7, and so on. And so the total is going to be 1 plus 3 plus 5 plus 7, all the way up to 2n minus 1. And it's a famous identity that tells you that the sum of the first 2n minus 1, or whatever, the sum of odd numbers up to 2n minus 1 is just n squared. And you can check that, it's easy enough. But we may even explain how you figure that out in the book or something like that anyway. It's actually not too hard to show. So it's going to cost you n squared flops to actually do back substitution. By the way, that's the same order as matrix vector multiply, right? So if you multiply a matrix, n by n matrix by vector, it's around n squared, maybe it's 2n squared flops, something like that. So back substitution is in the same order as that. Okay, now turns out now we can solve linear equations via QR factorization. So let's start with a matrix A that's invertible, so it's square, and we're going to solve AX equals B, which means to compute x equals A inverse B. So we start with the QR factorization of A. A has independent columns because it's invertible, so the QR factorization completes, and we write it as A equals QR. Q is square, it's an orthogonal matrix, meaning it's square and its columns are orthonormal. By the way, so are its rows. And then R. R is an upper triangular matrix with positive diagonal entries, and therefore it's invertible. So A is a product of two invertible matrices, and so the inverse, first of all, number one, we conclude A is invertible, number one. Number two, its inverse is the product of the inverses of the multiplicands in reverse order. So A inverse is going to be QR inverse, and that's going to be R inverse times Q inverse, but Q inverse is Q transpose. So that's it. So what we do then is now we know how to do it, because what we can do is we're going to compute this. We're going to compute x by back substitution. First, we're going to multiply by Q transpose B. We know how to do matrix vector multiplication. And then to compute x equals R inverse Q transpose B, we use back substitution, right? So that's kind of the idea. So here's the algorithm written out as some pseudocode. It works like this. A pseudocode, it works like this. We're given an n by n invertible matrix A and an n vector B. The first thing is you do QR factorization. That costs us, well, we'll get to that. That's 2n cubed flops, roughly. Then we calculate Q transpose B. That's a matrix vector multiply. And then finally, we call back substitution on this system of equations. We can do that because R is upper triangular with non-zero diagonal elements, and that's using back substitution. So step one here costs 2n cubed flops. Step two, that's a matrix vector multiply, that's 2n squared. And the last one, back substitution, is n squared. And so the total, what you see immediately is when you add these up, steps 2 and 3 cost very little. In fact, they're negligible because we're imagining n to be large. I mean, we're not thinking n10, we're thinking n 100, 1,000, 10,000. And what it turns out is that steps 2 and 3 are actually negligible because they're proportional, their order is n squared. And the first step is just this QR factorization. So what it means is that the real cost of solving linear equations is just QR factorization, which can be calculated by the Gram-Schmidt algorithm. Okay, so by the way, at this point, the Gram-Schmidt algorithm should be looking a lot more interesting. Earlier in the course, Gram-Schmidt algorithm was nothing but a numerical algorithm that tells you whether a set of vectors is linearly independent. Now, what we see is it can be used to solve equations, linear systems of linear equations. And that's great because that's already a whole lot of applications can be done this way. So the total complexity altogether is the second and third are completely negligible. That when you're doing a flop count, you would ignore something proportional n squared compared to n cubed. So it's basically 2n cubed is what the cost of solving ax equals b is for a and n by n matrix. And I'll give you some rough ideas about this. Let's do this. Let's solve ax equals b with a 1,000 by 1,000 matrix. Okay, so first of all, it would appear to be, at least to a person, that looks like a pretty big set of linear equations. We have 1,000 variables, x1, x2, x3, up to x 1,000, number one. And we have 1,000 equations in them, right? So altogether, the matrix A, which are the coefficients in a system of linear equations, has 1,000,000 numbers in it. I mean, I could make it sound like super, complicated and big. I can solve this in 1/10 of a second on my laptop, which is 5 years old. Okay, so that is just absolutely stunning, right? It's stunning. In fact, that's kind of very interesting part about this class, right? Is that we do these things, but they're actually like fully actionable, and you can solve a whole lot bigger, and it's a lot faster on other types of hardware, like on a GPU or something like that. It's very, very fast. But these are just stunning speeds so we can solve giant sets of equations this way. Okay. The next thing we're going to talk about is actually solving multiple sets of linear equations. And it's going to come back to this idea that of the 3 steps required to solve ax equals b, it's only the QR factorization of the coefficient matrix that actually costs anything. The others, I mean, they cost something in terms of flops, but they're negligible compared to the first step. So what that means is this. It's a situation where we're going to solve axi equals bi. I equals 1 to k. So I'm going to solve k systems of linear equations with a invertible. And so the right-hand sides are different. I have b1, b2, b3, up to bk. And of course, the solutions are different. That's x1, x2, x3. But the coefficient matrix A is the same for all of them. And so what we do is we're going to be smart, and we're going to carry out the QR factorization just once, okay? And then the only thing we're going to repeat is we're going to repeat for each right-hand side. We're going to actually do the back substitution and multiplication by Q transpose, right? That's n squared flops. And so the total is 2n cubed plus 3k n squared flops. And what you see is pretty stunning, that as long as k is like small, it basically is still completely negligible. And this is just completely weird and insane. This is one of the first things that you know is kind of shocking. So basically what it says is, well, let's take my laptop. Suppose I ask you to solve AXI equals BI for I equals 1 up to 10. Okay, so I want to do 10. I want to solve 10 systems of linear equations, and A is 1,000 by 1,000. And we already discussed that, and we found out that I can solve this in about 1/10 of a second on my laptop. Fine. Sorry, I can solve one of them in 1/10 of a second. Okay, so the naive method would be to just simply solve this 10 times, and that would give me 10 times 1/10 of a second, which is 1 second. Okay, but in fact, what this says is if I'm smart, I only have to, the only one I do, let's go back here, I do step 1 once, and then it's step 2 and 3 that I repeat 10 times. But the point is that what people would say is that the first step dominates, meaning it takes much more time to carry out the first step. And so what we conclude here is that I can solve, someone walks up to you and says, help me solve one set of linear equations, 1,000 by 1,000. I go, no problem, 1/10 of a second. And they go, cool, I'd like to solve now 10 systems of linear equations, same coefficient matrix. How long is that going to take? And you would normally think, well, a second. And the actual answer is 0.1 seconds. It's the same. So in other words, you can make the crazy statement, as a practical matter, I can solve 10 systems of linear equations, 1,000 by 1,000, in basically the same time it takes me to solve one. Okay, so that is weird. I mean, unexpected, but once you know all the parts, it all makes perfect sense. Okay, what we're going to do now is look at just a couple of very simple examples. There are many, many, many others, but let's take a look at them. The first one is in polynomial interpolation. So what we'll do is we're going to represent a polynomial that's p of x. It's a polynomial of one variable, scalar variable x. And I'm going to write it as c1 plus c2x plus c3x squared plus c4x cubed. Okay, so it's a quartic. No, it's a cubic. Sorry, it's a cubic polynomial. It has 4 coefficients. 4 because it also has the constant coefficient. So c1 is the x to the 0 coefficient. c2 is the x to the 1 coefficient, and so on. Okay, and what I'll do is I'm going to represent the coefficient, the polynomial, its coefficients as a 4 vector, c. Okay, so when you see a 4 vector now, it's going to represent a polynomial. Okay, and what I want to do is I want to find a cubic polynomial that satisfies these conditions. So when you evaluate it at minus 1.1, you should get b1. When you evaluate it at minus 0.4, you should get b2. At 0.1, you should get b3. And at 0.8, you should get b4. b1 through b4 are numbers that I have not yet specified. Okay? So, oh, and by the way, this is called polynomial interpolation because what it means is you want the plot of the polynomial, the curve of the polynomial, when you draw it, it should go through specific points. So it should go through the point minus 1.1 comma b. Okay, so that's called interpolation, when you go through these interpolation points. Okay, now we can write these interpolation conditions as, well, just a set of linear equations. It's AC equals B. Okay, and to check that, you would put C1, C2, C3, and C4 here, right? And see if this is what it's supposed to be. Okay, and then that's not A equals, I just get rid of that. There we go. Okay, so let's see if this faithfully gives you these interpolation conditions. Well, if you go across this first row, and with these coefficients, what you will find is that you are this first row of the product is actually evaluating P at the point minus 1.1. But that should be B1, and sure enough, that's the right-hand side. So this is correct. So these polynomial interpolation conditions basically I write as a set of 4 by 4 linear equations, a system of linear equations. Yeah, By the way, this would be exactly, even though this is like, it's from a computer's point of view, this is pathetically small. This is already way bigger than what any human being should do. Like, so, well, it's too late now, but if you had classes before where people, tortured you by solving like 3x3 sets of linear systems, that was really, in my opinion, a complete waste of time. And 4x4 would be off scale. So could you do this by hand using some kind of high school method, whatever it is, Gaussian elimination? Oh, you could, but it wouldn't be fun, and it's a complete waste of time. I should add that also. Okay, so if we solve this set of equations, we will get the coefficients. Okay, and in fact, we can even say this. C is equal to A inverse B. I should say a couple of things. This matrix has a name. A matrix whose rows consist of a number to the 0, number to the 1, 2, 3, up to certain powers. It's called a Vandermonde matrix, named after a mathematician named Vandermonde. And it is invertible. And it's invertible because these numbers were all different, right? So that's actually the condition. I haven't shown that, but that's the case. That's the idea. Okay, so this is just a compact formula that tells me these are the, you tell me what you want, where you want your polynomial to go through at these 4 points, and I'll tell you what the coefficients are. So that's how that works. Okay, so here, A inverse, this is to 4 significant figures. I mean, obviously it's more than this, but here it is. A inverse is this matrix here. And you look at it and you think, wow, well, okay, whatever. So if you multiply this matrix by this matrix here, you will get something close to the identity. Actually, because I've only given the other ones to 4 significant figures, you'd get numbers on the diagonals like 0.99999, and the off-diagonal entries would be super small, right? Okay, so here's A inverse. And let's see what it is. What's the interpretation of A inverse? Well, A inverse, and entries of A inverse map B, these are the values that your polynomial should take at these 4 points, into the coefficients. And so, for example, we would notice that these are like the smallest entries in the whole matrix. And what it says is, let's interpret that. So over here, I would put B, and then this would give me the C. This would give me C. And so what this means is I can say that the first coefficient is not very sensitive to what B1 or B4 is. Okay, well, who knew? But it's true. That's what this says. Another interesting thing is to actually interpret the columns, right? Columns are super interesting. Like, let's figure out what the first column means. So here's the first column. What does it mean? Well, that column is if I multiply A inverse by E1, I get the first column. That's true for any matrix. But wait a minute. E1 are the values that polynomial should take. And that says that the first column gives you the coefficients of a polynomial that satisfies this. At minus 1.1, it's 1. At minus 0.4, it's 0, 0, 0. This is like E1, the right-hand side. Okay, now that's got a name. A polynomial that is equal to 1 at a specified value and 0 at other values, that's called the Lagrange polynomial. And it's literally the coefficients of the, it's the coefficients of that appear in the column of the inverse of this Vandermonde matrix. Okay. And here's an example, and what we're showing you here is a couple of these. So first of all, this is us solving this for a couple of different cases. This is minus 1.1, and so for example, if you specify these values, this one, this one, this one, and this one, you'll get the polynomial. It'll go right through. It'll go right through those points because we've constructed it that way. So that's the idea. Here are the Lagrange polynomials. So here's the first Lagrange polynomial associated with these points here. And let's see how that works. Well, what it says is that you have 1 and 0. And so this first polynomial looks like that. It's a cubic. And sure enough, look at that. At minus 1.1, it's 1. At minus 0.4, it's 0. It's again 0 at 0.2 and also at 0.8. Here's the second Lagrange polynomial. Lagrange polynomial associated with these points is this. It's 0 at minus 1.1. At minus 0.8, minus 0.4, I'm sorry, it's 1. It is again 0 at 0.2 and also at 0.8. So these are the Lagrange polynomials. Okay, so, and each one has coefficients associated with the columns of the inverse of A.